Jay.
Jay Young.
I'm James Loeb.
And I'm Sarah.
Good day, everyone. So I'm Professor Charles Williamson. I'm going to show you different parts of a wind tunnel. I'm going to use the wind tunnel to investigate the drag of a blunt body, not a streamlined body, and hopefully with some messing around with some interference plates, we can reduce the drag by an amazing amount. We hope you'll think so too. Okay, so I'm now going to walk this way. Oh, hello, nice to see you again. Well, so here's the inlet to this wind tunnel. What's the cross section? It's something like 1.5 feet by 1.5 feet, something like that. But it's a really, for me, it's a really big, beautiful wind tunnel. That's why I call it BBWT, big, beautiful, big wind tunnel. Okay, so here we've got the flows coming in here, and it goes through honeycombs, just like you have with beehives, and it has a succession of honeycombs that are getting finer and finer, and screens, meshes like you have to keep out the mosquitoes in your back door. So it's a combination of these things. According to a recipe put together by Urbana-Champaign, and it's absolutely Illinois, University of Illinois, Urbana-Champaign, and it works incredibly well. What's it actually doing when we say it works? Well, it's reducing the turbulent structures in the flow, making it nice and smooth flow, and it gets down to root mean square turbulent structures, 0.01%. So that's really amazing. The other thing it does is it increases the uniformity. That is, it makes the flow speed at all different points in a cross section the same. So that's called uniform flow. Don't forget, that's not the same as steady flow or unsteady flow. Okay, so can I just take you down, take a look at the wind tunnel as we go? Okay, so these pieces of aluminium here are keeping the honeycombs and screens from getting sucked downstream. So the honeycomb screens are inside here, and then you have a big cross section going to a small cross section, contraction. And so, according to the conservation of mass, the flow speed here is slow, and it's very fast there. Where you make the flow go through a little hole, it goes faster. And so you end up with just extremely good, uniform, low turbulence, high-speed flow in this test section here made of lucite. That's this thing. So flow is going from left to right. The thing about this wind tunnel is it's different from other little tunnels you'll see in FM2, in that you have the motor downstream, and you have a centrifugal fan, which is basically, it's not blowing the flow down. This wind tunnel sucks. Sorry, I didn't mean that. This wind tunnel sucks sucks the fluid, the air is fluid, so we call it fluid sometimes. And it sucks the fluid down here. And so if you actually take the top surface of the test section away, you could get sucked into the wind tunnel, which wouldn't be very nice. So you wouldn't. So here you've got, in the test section, you've got a square section, cylinder or blunt body, and we're going to play with that. We'll come back to this point. I'm going to take you further down here, and we'll take a look at what goodies we've got here. Here's a square cross section still. You have to go past Evangelina. Let me get that right. Evangelista Torricelli. He's there, in case you're wondering. So you go from square cross section to round cross section, and there's been an increase in cross section area as well. So basically playing with the flow to make it ready to go into the centrifugal fan. So see you later, Evangelista. So this thing here is just a flexible coupling between this bit and this bit, so that our test section is not actually in touch with the vibrations coming from the motor. So you go through this thing, this bit here on the inside, you'll see that I'll take you, follow me down. I'll take you to see what we've got further downstream. James, you haven't seen this before, so it's kind of a new experience for you. So the fluid is coming down here, not through here, but all around the side here. And there's impellers or whatever, propellers. It's a centrifugal fan, basically. But it's also got a funny twitch to it. So why don't you put your head, not your whole body, just your head. You put your head in as far as you can go.
Further.
And say something. Ah! That's about as much as you can get out of this one. In 2 hours we can try and say, get something more intelligible. Than
And
that.
scream now to compare. No, outside.
Ah!
Yeah, so it's an amazing diminution of sound. So I'd like to show you the test section. If we were to follow the advice of the distancing group, then the first person you could have close to this thing would be out here. So you can't really do anything. You've got to get up close. At least one person has to get up close and see what we've got. What we've got here, I don't know if you can see that in the middle of this test section made of lucite, you've got an aluminium square section cylinder that was actually put together by Todd Fanciullo some years back, also an Italian chap. And it's a square section cylinder, this thing on the inside. And there's tiny little pressure taps, and the midway along the span from this side to that side of the tunnel, you can see a whole row, a vertical row of tiny little beautifully machined holes by Todd Fanciullo. It's absolutely a hero of mine, actually. And so we've got little tiny holes on the front side of the body and on the back side of the body. And it's these differences in pressure on the front and the back side that's going to give us the drag that we want to measure. And so I just to tell you a bit, well, okay, let me introduce an instrument here. It's just a tube that's facing upstream. Let me show you. It's called heterostatic tube. And I just want to show you, you've got this in your handout. Now I've got lots of big font again. I'm pretty keen on this font. It's called the Pitot-static tube, pronounced Pitot-static. Monsieur Pitot, he's around in the 1700s, so it's amazing actually what people were doing a long time ago.
Okay, so you have a similar diagram to this in your lab handout, but this is kind of a diagram that shows how the pitot-static tube works. So it has a hole at the front, which measures the total pressure at a stagnation point, which has 0 speed, and holes on the side, which measure the static pressure, PS, which is the pressure of the free stream. And you can see in this diagram that PT and PS, so the hole in the middle, which measures PT, kind of goes into an inner tube, whereas the holes on the side, which measure PS, go to an outer tube. So these two measurements remain separate. So the pitot-static tube can measure both PT, which is the total pressure, and PS, which is the static pressure. So using Bernoulli's equation, you can work out that PT minus PS equals to 1/2 rho U squared, which is your dynamic pressure. And so using a pitot-static tube, you can not only measure PT, PS, the dynamic pressure, you can also figure out what the velocity of the flow is.
Let me show you where the pressure taps go to. So they're on the front face and the rear face of the cylinder, halfway along the span. And then the little pressure taps attached to what's it called? Hypodermic tube. And these are all attached to Tygon tubes as they come out from the cylinder at this point where my hand is. So all these, look at this stuff. You get something wrong. We had somebody who got this wrong. They spent 10 years trying to sort it out. But basically those tubes come down here. What you do in this machine here is you measure, actually I'll show you, static pressure down here is this tube here. Measuring total pressure with this tube here. So what you're going to try and do is everywhere we measure pressure, you're going to measure it relative to the static pressure. So you're getting P minus PS, and from Bernoulli's it's half rho U squared. And then on the other side, you're going to start off by measuring PT, comparing it to PS. Then, as we turn this thing around, we're going to sample different holes one at a time. I'm going to press this thing. So this thing turned one little increment, and now it's measuring the pressure at another one of these tubes in a different position. And so you end up measuring P minus PS, P at the point of interest minus PS, or PT minus PS. And eventually I think, I'll show you how you get from that to pressure coefficient in just a minute. So I think you've got this on one of your pages here. So this is just a diagram of cross-section of this square section cylinder, and it's giving you the locations where you're measuring pressure on the front and the rear. So it's quite a lot. I think it's about 20, between 25 and 30 something.
22.
22. Gosh, you're a fast reader. Oh, you read this bit? Yeah, okay. So then this round thing here is telling you all the locations where we're extracting the pressure and comparing to static pressure. And I just want to show you about the pressure coefficient, because it's quite strict the way this thing works. But the bare certificates, okay. Pressure coefficient is the difference in pressure in a system. You can define pressure coefficient as difference in pressure over dynamic pressure, which is called half rho times velocity squared. And so when you actually measure a pressure coefficient, you measure P minus PS, and you divide by half rho U squared, but that's the same as PT minus PS. And all these things, P minus PS, PT minus PS, they're just voltages that are coming out from the front of the transducer here. This anemometer, this thing is the pressure transducer. Just to let you know, there's a little diaphragm in there that is able to get pushed one way or another due to differences in pressure on each side of the diaphragm. There's different ways of getting from that point to an actual pressure as well. So basically, through this table here, I'm not going to go into detail on this. It's not worth it at this point. But basically, when you want to get a drag coefficient, you're measuring coefficient of pressure times little areas each time. And because of the geometry of the setup, you get weighting functions here that are equivalent to little areas. So basically you're measuring pressure coefficient or pressure difference and multiplying it by area over which that pressure is assumed to occur. And then you get pressure times area, and you get little bits of force. And in our table, can you turn over the page? Nice. Okay, so on this table, which looks a lot better than the one I've got here, you've got the first column is scanning valve location, telling you which pressure tap you're actually measuring. Then this tells you how much, so you enter into this column the actual measurements that you get off the anemometer and the transducer. You enter that into this column, then you multiply that by y over h, the location, and then you also evaluate the P minus PS or PT minus PS, go down this column here. Basically, you're trying to get a pressure times an area, and you've got that in the second, in these, sorry about my hand jumping. You've got pressure coefficient here, and you've got the weighting function here. That's pressure times area, and when you multiply them together, you add them all up, you get the total drag coefficient of this body that you're looking at in the test section. Just in case you have problems with the eyesight, like I do, I've got switch on motor, and I think it's font 636 on my computer, so I love it. This is the kind of writing you want on a Christmas card to your mother. It means you can only write 2 lines, you save a lot of energy that way. So anyway, this is my instructions to switch on the motor. So rather than me do it, can I pick on somebody who's at least 6 foot away from me? Jay, can you go and switch on the breaker circuit?
Yes.
That's what it says to do. You turn it quarter of a turn clockwise. Oh, can you see that? It's always a good start when you hear the noise of little fans going on. So the panel control light flashes. So this is just panel control. Yeah, I look at control here. Once that's done, you press the up button to get 15. You've got it set up. When it goes on, it's going to go to a favorite velocity. 15.0 hertz, that velocity. Anytime you will. Okay, I think you've got pleasure of pressing the run button that button there. See what happens. Yeah, it's always a nice thing when you actually see it. So that sounds really good. It's got a fantastic rumble if you go up downstream or upstream. It's like a little aircraft itself. It's really, yeah, big wind tunnels that they've got at NASA Ames. You can put an actual jet aircraft in the test section. Have you come across that one? Have you seen it?
Yes.
Yes. There should be 3206. Okay, so now we go to the handout that all you guys have got. We say, what do we do now? So the next thing, rather than try interference in different plates and cylinders and so on, we've got time to do all that. We're not going to do it all. But the first thing we're going to start off doing, we've just got a bare cylinder with no structure flow. We're just going to measure the pressures on that to get the bare cylinder. Not bare as in neutral, bare. B-A-R-E, that's B-E-A-R. So we're going to be measuring pressures at this point. We're going to enter P minus PS in the fourth column, CP in the fifth column, multiply that by the weighting functions, which is multiplying the pressure times the area. Gives you little elements of force. You add all those CP times weighting functions in the right-hand column. You add up all these data points that you get here. When you get to the point, you should get an accurate determination of the drag coefficient of a bare cylinder. So let's see if we can do that. Just before we do that, we're measuring 0.56, 0.57. We've done this experiment. We've changed the experiment every now and then. But we're now back to my favourite experiment, which is wake interference. And if you go down here, well, no, let's look at P minus PS, or PT minus PS. It says 0.598. This is in 2009. It's a long time ago. And it's 0.56 something like that. So this wind tunnel has been moved from between 4 buildings, and it's still measuring down to 2%. So it's absolutely fantastic. It's very rare that you get something like that. No matter what you do to it, this thing just keeps working. Anyway, so I think let's take some data, everyone. So we're going to measure P minus PS. Do you want to operate this thing and I'll write something down?
Yeah. So 0.56 for the first.
You give us 3 digits. That's fine.
Okay, 0.560. Alright.
Okay.
So moving to pressure test location number 3, we have 0.050.
So this is all going into this table here. So keep tracking.
Location number 4, we have 0.265.
Right.
Alright. Pressure point number 5, we have 0.374.
Okay, let's see what we had. Oh, that's press down number 5.
Yeah.
It says 1396 here. You're out, but people said we were off. Okay, no, this is great. Keep coming in.
Okay. So for pressure point number 6, we have 0.440.
Pressure differences, that's good.
For the next one, we have 0.489.
Okay, just a bit out.
For the next one, we have 0.514. For the next one, we have 0.534.
Yeah, keep going.
0.550, point number 10.
Right, super. I should sit down and you work behind. What do you got?
We have 0.555.
So the difference between pressures is getting smaller and smaller, isn't it?
And we have 0.562 for the last one on the front face.
Okay, so before you go further, I'm just going to ask you a question. So to start with, when we measure PT minus PS, we got 0.560. Great. And once we get the pressure tab right in the center of the front of the cylinder, we get 0.562, which is very, very close to 0.560. So basically it's telling you that if you have a stagnation point, PT minus PS measures pressure difference at stagnation point. Therefore we're expecting, so what does that tell us about where we are in the flow in the cylinder?
We're dead middle.
You're dead in the center, right?
Yeah.
So it's another stagnation
Yeah.
point. It's not exactly a stagnation point because it doesn't move up and down. It's to do with the vortices that are forming behind the body.
Yeah, so at this point you might have noticed that we've only measured data for positive y over h's. So you can see on the page the y over h's span from 0 to 0.45. And if you go back a couple pages to the pressure tap locations, you can see that locations span from minus 0.5 to positive 0.5. So a natural question might arise as to why we aren't measuring the negative side of things. The reason for that is because our square cylinder is symmetric. So any data that we measure for the positive side will be symmetric on the negative side. And so if you look closely at the Tygon tubing, you can see that for each one of the tubing that leads to the pressure transducer, there's actually two tubes that lead to that. And so each of the tubes comes from one from the positive side and one from the negative side. And so our data is actually the average of both the positive side and the negative side.
Okay, thanks for all that. So in all the measurements you made so far, we're measuring the pressure on the front side of the body. Now, it's the difference between the pressure on the front and the pressure on the back. When you integrate it over area, it gives you the force, the most interesting. So we're just about to go from the front phase, where we had that the stagnation pressure, the total pressure on the front phase, to the back of the surface, back of the body. So if you want to press your button, brilliantly done, by the way. Thank you, Jay, very much. So what have you got for a number?
So I've noticed that the number has gone negative now.
Right.
And it seems to be jumping around quite a lot
It is.
compared to the front face, but it seems to be around minus 0.927.
So that's it's very, so what do you think is going on the back face of the cylinder? Giving you this very turbulent.
Right.
I think I've given the game away.
Yeah, so something interesting must be going on with the vortex dynamics behind the back of the cylinder that's causing this value to jump so much compared to the front face. And we'll discuss that later on in the lab.
Yeah, we will actually.
Yeah.
So, and then you get a minus sign, but the weighting function, because you're on the back surface of the body, also has a minus sign. So the minus times the minus gives you a plus. So, that's giving you a big contribution to the drag. Okay, can you press the button a few times?
Yeah, looks like it's around the same value of minus 0.915.
Okay, and then I'm just going to say, for the purpose right now, that you go all the way right to the very rear, at the middle of the rear of the body, and the pressure is remarkably constant as you traverse from the top to the bottom of this back surface of the cylinder. So yeah, when you add up all the P minus PS's, the pressure at different pressure points P, you add those all up, you multiply them by the weighting function, and you add everything up at the end. We don't know what you get. Do you want to go into the note? We go through it, it's going to take a bit of time. But typically, because we've been playing with this thing for the past couple of days, you're going to get something like 2.342 the numbers that we got in two buildings back in history, it was 2.336 or something. So it's really, I don't mean to show off or anything, but it works so bloody well. And all kudos to the people at University of Illinois for their system of screens and mannequins. It really works well, giving you good flow quality.
So this is just an interesting little side point, but on the next page in your lab handout, you'll see the pressure distributions for both the front and rear faces of the bare cylinder. And one of the cool things that you can do is figure out what the drag is graphically by essentially finding out what the area is between the front face and the rear face on the cylinder.
So now we've got the bare cylinder case. Meaning we don't play with the flow in front by putting an insurance plate. We can go ahead and do that with the insurance plate. So, Jay, what have you got? What experiment are we going to do now? Go to the front page of this handout. We've done part one, which is CD and CP, but we haven't actually got the numbers yet, but that's okay. For the bare square cylinder. These are the different various positions that we're going to place the interference plate and see what that does to the pressure distribution around the cylinder. You'll see, because we'll take the camera and look at what's happening in there in just a minute. This thing here, we're going to put an interference plate on this rack and pinion. It's called a rack and pinion, like you have in the car. So I'm going to place one interference plate between this point and the other point. We're going to move it back and forth in front of the cylinder. See what happens. Shall we try that? Okay, we're going to place interference plate between this point and this point of the rack and pinion system. Move it upstream and down to different locations and change the width of the plate. Now, the distance between the plate and the cylinder is called G for gap. Gap with a P at the end of it. The width of the plate is called P, and the width of the cylinder is 2 inches, I think it's called H. So we're going to vary G over H and P over H. These are non-dimensional gaps and width of the cylinder. I'm going to go the other side.
So this is the first plate that we're going to use. Its height is 13% that of the square cylinder.
Okay, so here with the rack and pinion system, we managed to put a plate and it's half a cylinder height upstream of the front face. That's like G over H equals 0.5. And it's parallel to the body. So we're going to trip up the flow in a way, going around this and send that same flow onto the front face or the sides of the cylinder and see what happens when we measure pressure and drag coefficients. So we'll try doing that right now.
Alright, so now we're going to be using a LabVIEW VI to measure the pressures that we did manually by hand earlier. And so when we click run on the VI, the first question it asks is, please move the scanning valve to the home position.
That's now my job. I think it's looking pretty good. It looks like it's at home. I think we're ready to start. Anything else it says?
Okay, so I'm going to click OK here. And it asks a follow-up, are you absolutely bloody sure the scanning valve is in the home position? And
the answer is, again, yes.
So now we can click yes again, this time with an exclamation point.
Nice.
And so now you can see it's now sampling each location using the LabVIEW VI, and it will record that data to an Excel spreadsheet, taking out the manual process of it.
22nd pressure tap, then what's left for us to do then? What would we be doing? We'll be putting it through the system and trying another data point, right? Trying another change of variables.
Yeah. So once we go through all 22 pressure taps for this G over H, we're going to change the G over H. If you're following along with your lab handout, this is for G over H of 0.5. We're going to be doing it for 1.5, 2.5, and 5.0.
Yeah, different gaps, yeah.
Yeah, for this plate height, and then we're going to exchange it, the 13% plate to the 37% plate, and run it at the same G over H's, except instead of 5.0, we're going to run it at 4.0 and 6.0.
Okay, what do we got to do? What has rack opinion got to do this time?
So we just finished collecting all of the data for the G over H of 0.5. So I'm going to continue following these instructions. It says to open the squared data Excel file.
Great,
So
great.
I'm going to do
see what
that.
See what the drag coefficients look like.
Yep. And yes, leave this file open. And this one.
Oh, very nice.
So
what was the no, because we didn't work out the drag coefficient in the bear case.
right, we're going to give them the drag data for the
Did we work it out? It was 2 point.
2.4 or something? Right?
2.342.
Yeah.
So that's 2.342 drag coefficient for a bear case. For the bear case, hello. 2.342. So now we put it roughly at 10%, 1/10 of the height of the cylinder, wake interference plate on the front, and we're going to see what effect that has. We can see what effect that has if we look here. CD is 1.652. So we've had just look. I wish. Can you come back over here? I don't know if I could just remind us that we're talking about a very tiny little plate here. From this angle, you can see it really well. Okay, so we've had a huge effect on the drag coefficient. So shall we try another G over H value? Okay, I'm sorry this is not very still, but we're trying to do run number 1, 2, 3, 4, etc. We're going to vary G over H, so at the moment that puts you in your page there. Do you need a pen? Anybody got a pen? There you go. So let's fill out this. So G over H 0.5. CD is
1.652.
Okay, and what's CD over CD? What was CD there? 2.342. And that's effectively for G over H equals 0. Like the plate is so close to the body that it's
part of the body at that point.
Exactly.
So
we've got getting some data into this table, and I know it's done by hand, but there's no problem with that. It's going to give us some really interesting results. Has anybody got a calculator?
What is it?
1.652 divided by 2.342.
0.71.
0.71. And that's this CD. That's CD over CD there. Okay, so what they then do, is we're going to do this.
And I'm going to bring a sheet here. So the first couple lines look like this.
And do it as a bullseye, because then you can see it. If it's a dot, you can't see it. So bullseye there, and then 0.5, 0.7, what was it?
0.71.
0.5, 0.74. Okay, we've now entered.
Give me.
That's our first data point. Don't forget, you've got that drag reduction there. And the width of the plate upstream is almost 1/10 of the width of the cylinder. So that's pretty amazing. Okay, well let's change the position of this.
for P over H of 13% and G over H of 1.5, CD is equal to 0.71.
Nice.
So you can see by the addition of the 13% plate at a G over H of 1.5, CD over CD bare is 0.3, which means we've managed to reduce the drag over the bare cylinder by 70%. And we will see what happens as we keep moving the plate.
Later.
So for our 13% plate at G over H of 5.0, CD is equal to 1.286, and CD over CD bare is equal to, J?
0.55.
0.55.
Excellent, guys. Good teamwork, good teamwork.
So what you just saw us take was all the data for the P over H of 13% plate. Now we're going to be switching to the 37% plate, so you can see it's much taller than the 13% plate. And we're going to...
But still, the plate width over the cylinder width is still
Right.
1/3.
Yeah,
Right.
yeah, it's barely over a third of the height of the cylinder.
6.5 hours later.
So we've now run through the 37% plate, which is a P over H of 0.37. And we've done this for a number of G over H again. So we've done G over H of 0.5, 1.5, 2.5, 4.0, and 6.0, and calculated CD for each of these, and CD over CD bare. And we can see, if you look, for example, at a G over H of 2.5, a CD over CD bare is 0.04. So this means that by having a plate 37% the height of the cylinder at a G over H of 2.5 in front of it, we can reduce the drag on the cylinder by 96%.
Absolutely ridiculous. I mean, it's absolutely amazing. But that's not the end of it. We've got another two really nifty results coming up. If you plot all these things, CD divided by the bare, CD for the cylinder with the plate in front, divided by CD for the bare case, is this CD over CD bare thing. And you can see that for the 13% plate and the 37% plate, it's such a mess, you almost can't find any curves to go through, but we'll interpret that for you right now. I'm going to put the curves through and through these data points, and you'll see what sense comes out of it. That's the 13% plate. So there's something going on here. You seem to be wanting to go out through the bottom right here. And then the curve that goes through, could you hold it? Sorry guys. The curve that goes through these two data points here continues along here. So there's like a mismatch. They don't meet each other. I mean, if you force them to, you just can make a curve from here to here, but that's not what's happening. We've done a lot of these different cases, and they all have a characteristic left-hand branch that goes down beyond the right-hand branch, and then the right-hand branch starts further up. So this kind of overlap of two solutions in this region here.
And let's see what it looks like when you do the same to the 37%.
Yeah, okay, well go ahead, let's try that. So here's what our interpretation of these two data sets in different plates. So with the 37% plate, you've got this 95% drag reduction here at these different gaps between the plate and the cylinder. That's just crazy. That's a crazy result. It's not the craziest, we'll show you. But basically, if I could just keep this still. There you've got this left-hand branch way down in CD, and then there's a jump in CD to a higher branch as you increase the gap ratio. I mean, you would know by common sense that it has to go from this. Ultimately, it's going to go all the way up to here. So this is just it making its way up in a little step. But these curves, these solutions, overlap each other. What would that be called? Where you have solutions that overlap each other. If you come in from the right, you're on one curve. If you go out to the left, you're on another curve.
Hysteresis.
Let's say it again.
Hysteresis.
Hysteresis. Well done, everybody. Hysteresis. So, spelling hysteresis is difficult to start with. But in fact, there's another possibility, which is what it's actually doing. It cannot exist stably on either the upper or the lower curve. What it does is it jumps backwards and forwards. So actually, when you make the measurements of the drag, then you get intermittent switching between two solutions. And it's absolutely fascinating. At least it is, depending on who you are and what you're like. It's maybe not fascinating to everybody, but it's an amazing result, they're all the same. So I'm just going to finish that off by shading in the region where you have intermittent switching. And then I think we're done with this. But we've still got some more to do. So I haven't put their names here, but I put mode and here's one mode, and here's another mode. And that shaded region is showing you the sort of intermittent switching regime, where you can be on one curve or the other curve. And it jumps backwards and forwards in the shady region. It's never kind of satisfied. So we were getting results like this with the mode over here, which led to a bigger drag reduction. And the mode on the right is less drag reduction.
And in the middle?
In the middle is kind of intermittent switching between two modes. But can you remember what the name of the modes were from the lecture, from the pre-lab?
Jay, what's the first mode?
So the one that results in greater drag reduction is cavity mode.
And the other mode?
The one that results in lesser drag reduction is the wake impingement mode.
Correct, right, correct.
Yay!
And so can you sort of physically show people, talk about that for a second? Okay, so we did some flow visualization using a smoke wire that would be very nice for you guys to try out that smoke wire. It's actually part of this course. But doing smoke visualization is apparently ridiculously good fun, I can promise you. You can do it with your iPhone or anything. You just need smoke and then something to capture the visual. Can you hold me outside this? It's going to fall down. Thanks, Jay. Okay, so this is just some stuff we did with a cylinder which is circular, not square. And I think as you increase the distance between the circle between the circular shape and the little plate that is further upstream, you can see as we go down here, so the position of that plate moving further to the left, and the cylinder moving to the right. You're getting in here a region in between the plate and the cylinder that doesn't have this unsteady vortex shedding, the creation of opposite sign vortices one after another. It doesn't have that until this gap is sufficient to allow these alternating sign vortices to occur. So here they're nice and steady. You get counter-rotating pair. It's kind of like it's going like this. It's counter-rotating pair of vortices. And they're trapped in here, they can't come out. And they're providing these sort of very vigorous counter-rotating pair of opposite sign vortices. So you've got a lot of low pressure here. You've got low pressure in front of the cylinder and low pressure behind. So the drag of this is almost zero. Not quite, but. And then as the gap between the plate and the cylinder gets big, then you've got enough space to put a Kalman vortex street, alternating sign system of vortices between the plate and the cylinder. So I think we still have one or two experiments just very quickly. Just let's see what we've got.
Okay, so we just finished taking all of the data for the 37% plate. Now we're going to be swapping it out for the 50% plate. So you can see it's taller than the 37% plate. As the name suggests, the height is 50% that of our square cylinder.
So now the last one we are doing is P over H of 50%. And it's going to be at a distance G over H in front of the square cylinder of 1.5.
Moments later.
Hey Skipper, can you come over here? I think there's a problem with the data.
What we had so many problems this afternoon. It's an extra 3 hours on Christmas. We've only been here 4 hours.
Yeah, look at this drag coefficient. It's negative.
It says minus 0.09. Oh no, negative drag. What do you think we ought to do? I mean, everybody here, which are two people, but what do you think we should do?
Redo it.
There must be
Do
something.
you guys think we should redo it, or we just like accept something which could be wrong? We don't know.
I don't know. There must be something wrong with the equipment. The negative drag coefficient doesn't make sense.
I think I'm sorry about this, guy.
Yeah.
It's going to hold things up, but we've got. I just want to pull this down so you can see I'm very serious here. We've got to go back, and I think we better do this again. This is fun. What's your feeling?
I think that's the only way to progress.
Oh my God, I spent so many hours here already.
More moments later.
Okay, so what's the result now? We're trying this thing again. What do you find?
It's still negative. It's still 0.091.
0.091. Okay, so it's very, very close to the value we had before. So we're going to have to accept that. Well, now, how can that be real? It's crazy.
I don't know. How can it be real?
There's too many of us throwing our hands up in the air.
What is negative drag?
So we're not creating thrust on the cylinder, is what this data is suggesting.
That does seem to be the answer, yeah. Instead of plus drag, you're getting some negative drag, which is thrust, yeah. No, that's
So how could we be having thrust on our square cylinder?
yes, exactly. I keep having to... You ask the right questions, and I'm just a yes man. Yes, exactly. What's the explanation?
Well, since we can't be creating energy in this system, otherwise we'd all be billionaires, then the drag must be on the plate in front of the cylinder. That must be eating most of the drag.
Well, the plate's eating a lot of drag, but how come the drag coefficient of the cylinder itself is now negative?
Yeah.
What does that mean physically?
So what does that mean about the pressure on the front face of the cylinder compared to the back face of the cylinder?
The pressure on the front face of the cylinder must be less than the pressure on the back face of the cylinder.
But how could that be?
Must be.
Yes, how could that be? Sorry.
We must be in the cavity mode, and the recirculating vortices in the cavity mode must be stronger than the vortices on the back of the cylinder, creating stronger negative suction on the front than on the back.
That's very detailed and it's very good. I mean, absolutely, that's just incredible. I mean, I have to put my hands on the cheek to understand it. Yeah, so the pressure on the front face is lower than the pressure on the back face. Numerically, there's no reason why I shouldn't do that. There's nothing in nature that says that's not possible. So, if you actually had this thing on wheels, you had the plate in front of it, you could entice the cylinder to move upstream. You know, this experiment you can actually do. No, I think that's amazing. So, of course, you know, what's the question one has now with this whole system? I mean, have we invented something? Have we invented something absolutely radical?
So Jay, you were saying this before.
Right. There's no way we created energy. The drag.
There was some argument there, yeah. So, what's like the question that people, when they're leaving, they're going to be thinking? Okay, so you've got a thrust upstream. I can't remember what I was going to say.
I think Jay, you know what I'm getting at here.
Yeah, so we have to consider the drag of the entire system,
Yes.
and now the plate is part of the system. And so now we have to look at the drag of the entire system rather than just the cylinder itself, because the cylinder itself doesn't tell the whole story.
Exactly. So that's something that we can go ahead and investigate before we meet again. So, CD system over CD pair.
Which is a nice segue.
Exactly.
So now we're going to go over the expectations of what plots we want you to have completed before your tutorial. So as you can see, the first plot that you'll be doing is looking at the actual pressure distribution versus potential flow. And you're going to do this for the data that we took for the bear case. And as you can see, your real data is going to be discrete data points. And then the potential flow data is going to be from your lab handout. on the second last page. So you can get the data from that second last page. Make sure you have a citation of where this data is from, and you're going to put a spline fit to that data. And make sure you label the front and rear faces. The second plot is looking at CD over CD bare versus G over H. And you're going to do this for both your 13% plate height and your 37% plate height. So what we want to point out here is this little comment on the side where it says schematic only, there may be discontinuities. So recall when we looked at this in the lab, this is where we saw our cavity mode, our intermittent switching, and our wake impingement mode. So make sure you don't have just a continuous line for the 13 and 37% lines. Make sure that you have your cavity mode and label cavity mode, your box of intermittent switching labeled, and then the wake impingement mode at the end also labeled. And make sure you label the 13% and 37%. And apply a spline fit to these data points. So the last one on this first page is the pressure distributions using interference plates. So this is going to be two different plots for your 37% plate data. So you're going to have one plot of G over H equal to 1.5 and one plot of G over H equals 4.0. And what we want you to do in these two plots is make sure you have the same axes bounds on each of the two plots. So as you can see, as a guideline, perhaps you do CP as negative 2.5 to 1.5 on the y-axis, and your y over h of negative 0.5 to positive 0.5 on your x-axis. Have these bounds the same in each of the two plots. So you notice on these plots as well, you're going to be comparing it to the bare case. So your discrete data points here are going to be your 37% plate data, and you can put a spline fit to that as well, and make sure you label the front and rear faces of your 37% plate, and you're going to shade in between the front and rear faces and label that as CD. You can also see this continuous line here. That's going to be comparing it to the bare data, and again, make sure you label the bare case front face and the bare case rear face as well. So on the next page of your handout, you see that we have a table for optimum drag reduction. So we want you to fill this out with your data for the 13% P over H plate and the 37% plate. So you're going to put in your CD over CD bare, the minimum CD over CD bare for these two plate heights. And then you can see at the bottom of the page here, there's an equation for CD plate. So it's the 1.369 P over H plus 0.862. And this equation actually comes from the last page of your handout. So you can see this at the back from Purdy and Sheridan. But you're going to fill out this table with CD plate for all of the different plate heights in this table. After this, you're also going to fill out CD system over CD bare for each of these plate heights. And the equation for CD system over CD bare is found at the bottom of this page. So you're going to need this table to do the last two plots. So we're now looking at the next page of the handout with plots 6 and 7. So the first one you're going to do is your minimum CD over CD bare. So that was the second column in that table. So when you do this, you're going to do minimum CD over CD bare versus P over H. You're going to do a spline fit to these data points and have a line at 0, and make sure you label that for a positive value, so positive minimum CD over CD bare, you have drag, and below this you have thrust. So make sure you label drag and thrust. The final plot that you will do is the minimum system drag versus P over H, and that is the final column of the table on the previous page. Again, you're going to do a spline fit to these data points. So we have CD system over CD bare versus P over H. And on this plot, we want you to mark at what P over H you have minimum drag.